Okay, so in this lecture, we are now going to use the data that we had from the Measuring Gravity lab to start talking about how we can use that to calculate how fast an object would accelerate if I just dropped it, instead of rolling it down an incline if I just dropped it. Okay, and I want to say right off the bat that I have not checked these calculations ahead of time. I'm sort of doing this in a time-saving mode, and so I might get good results or I might get poor results because you are getting non-cooked data. I'm just doing it and seeing what we get. Okay, so this is what we had from before, but we're going to do some other stuff with it. Okay, we're going to start talking about vectors. Now, I had an incline like this, where this is 0.05 meters, and this is 1 meter, and this is 2.9 degrees. And we had a cart. Now, what we actually want to know is we want to build a triangle with accelerations, because accelerations are vectors and vectors are objects that have direction. Well, in our previous lab we determined that the acceleration of the acceleration of the cart down the incline was 0.48 meters per second squared. Okay, now right off the bat I'm going to tell you, because I know where this joke is going, I can see that it's actually going to work out pretty well. So what I'm going to do is I'm going to draw an arrow down the incline, and I'm going to label that arrow 0.48 meters per second squared. Now, if there was no incline whatsoever, if I could just snatch that incline out of there rapidly, the cart, instead of going this way, it would actually go this way. And how fast would it go? Well, its acceleration would be g. It would be the acceleration due to gravity. If I could just pull the ramp out, the cart would just drop down with an acceleration equal to gravity. Now I'm going to connect up this triangle, and here we're going to call this later. We're not going to come in with this right now, but I'm going to call this force normal. We're not talking about forces yet, so it actually isn't really for right now I'm going to ignore what I just drew right there. But that's going to be force normal when we talk about it later, and the normal force is always perpendicular to a surface. So the surface of the incline is right there, and force normal is perpendicular to the surface. I really want you to say out loud, force normal is perpendicular to a surface. Or actually just say normal is perpendicular to a surface. The word normal, I'm going over this several times, and it's really, really important. This is something a lot of people don't remember, and they have a problem with. Okay, now I'm going to do a little geometry here. Okay, this is a 90-degree angle, and this is a 90-degree angle. So we actually don't need this part right here. And so we have up here, we have an angle. Now that angle is congruent to itself. So I've got a triangle 1, 2, 3, and I've got another triangle 1, 2, 3, or actually I should probably do 1, 2, 3. I should go this way. 1, 2, 3. Now, this angle appears in both triangles, and so it's congruent to itself. And then this is a 90-degree angle for this triangle, and this is a 90-degree angle for this triangle. And so we have two angles that are the same, and so that means that the third angle needs to be the same. So that means that this angle has to be the same as that angle. So I'm going to write 2.9 degrees. Okay. Now, right now I've got a right triangle here. So this is the right triangle that I want to work with right now. The right angle is here, so the hypotenuse is over here. So I have opposite and hypotenuse and the angle. And so what I can do is I can do sine of theta is equal to opposite over hypotenuse. And so I can do the sine of 2.9 degrees is equal to 0.48 meters per second squared over g. And I can solve that for g. But I'm actually not going to solve that for g that way, because this 2.9 I'm not really comfortable with the level of error in that 2.9 and then the level of that rounding. What I'm going to do is I'm going to go with similar triangles. The similar triangles that I'm going to use is this triangle is similar to this triangle. So I can do ratios. I can say 0.05 meters is to 1 meter as 0.48 meters per second squared is to g. Now, I really don't like having my variable in the denominator of fractions. So what I'm going to do is I'm going to take the whole thing and I'm going to flip it. I'm going to flip the fractions, and so I'm going to say, let's put it right down there, 1 meter over 0.05 meters, I should put a 0 out in front of there, is equal to g over 0.48 meters per second squared. Now, work that out, see what you can get. I'm going to get g equals 0.48 meters per second squared times 1 meter all over 0.05 meters. These meters are going to cancel out, and if I do this on my calculator, I'm going to get 0.48 divided by, I don't have to do the times 1, divided by 0.05, and I'm going to get 9.6. So I'm calculating that g in my lab is 9.6 meters per second squared. Now, some of you by now should know that the official value for people who are doing it with equipment that is much, much, much more accurate than my setup. My setup is very inaccurate, but you should know that the official value for g is 9.81 meters per second squared. That's official. So I got close. I think I got reasonably close. I'm happy with that. And I'm going to end this video right here.